So we're going to take a look at a problem of finding a greatest common divisor using the Euclidean algorithm for polynomials. We're going to start off with 3x cubed plus 4x squared plus 3 and 3x cubed plus 4x squared plus 3x plus 4, and we're going to consider this in the field, the polynomial ring whose coefficients come from the field F5. Remember that Z mod 5Z. And so we start out, here we have two polynomials each of degree 3, so we could divide either one by the other, and we're going to do both orders to see how we can get two different results, or seemingly different results. So we set up our long division of polynomials here, and we say, well, how many times does 3x cubed go into 3x cubed? Well, it goes in there one time, and then we have 3x cubed plus 4x squared plus 0x plus 3 to subtract off. We're left with 3x plus 1. At this stage, that's a remainder because the degree of 3x plus 1 is smaller than the degree of 3x cubed plus 4x squared plus 3. So we can't do any more division. So the Euclidean algorithm says now we need to take and divide 3x plus 1 into 3x cubed plus 4x squared plus 0x plus 3. And that goes in x squared times initially, and so we get 3x cubed plus x squared, subtract that off, we're left with 3x squared plus 0x plus 3. New term to the quotient is x, and when we multiply that, we get 3x squared plus x, we subtract, we now have minus x plus 3. And there's a temptation to stop here because it's not obvious that we should be able to divide 3x plus 1 into minus x plus 3. But remember that the division algorithm, or division theorem, says we're only done when the degree of the remainder is strictly smaller than the degree of the thing we're dividing by. So we're not done, because the degree of the remainder is 1 and the degree of the thing we're dividing by is 1. So somehow we have to figure out what can we multiply 3x plus 1 by to get a leading term that's of the form minus x. And thinking about it a bit, minus x is the same as 4, so if we multiply 3x plus 1 by 3, that would give us 9x plus 3, but 9x is just 4x in Z mod 5Z, or an F5, and so that works out, and now we have a remainder of 0. As soon as we have a remainder of 0, we go back and we look at our last non-zero remainder, and that is a GCD. So a greatest common divisor here is 3x plus 1. So how do things change if we do our division the other direction? So let's take a look at dividing 3x cubed plus 4x squared plus 3x plus 4 into 3x cubed plus 4x squared plus 0x plus 3. So again, quotient of 1 initially, and we go through and we subtract that off, and we get minus 3x minus 1, also known, maybe for better or worse, as 2x plus 4. Now the degree of 2x plus 4 strictly smaller than the degree of the thing we're dividing by, so we need to go do another division, and so now we want to divide 2x plus 4 into 3x cubed plus 4x squared plus 3x plus 4. And so here, this is a little less obvious, but it's tied in with what we saw a moment ago, so now we need to multiply 2x by something so that we are looking at 3x cubed. And so if we were working with rational numbers, we'd multiply it by 3 halves, but we're in F5, so we don't quite have that. But the inverse of 2 is 3, and so if we multiply by 3 and then by 3 again, we should have 3, so we're multiplying by 9, which is 4, and hey, yeah, 4 times 2x is 8x, which is, 4x squared times 2x is 8x cubed, which is 3x cubed in F5 adjoint x. So that's what we're looking for. So we need to start with 4x squared, and we'd have 16x squared, but that's just x squared in F5, do the subtraction, we're left with 3x squared plus 3x plus 4. Hey, this isn't so bad. We know that if we multiply 2 by 4 in F5, we get 3, so we'll multiply by 4, and we get, and we multiply by 4x actually, and so that gives us 3x squared plus x, and we're left with 2x plus 4. Hey, I know, we just need a 1 at this point, and now we've got a remainder of 0, and so we've got our GCD, a GCD as 2x plus 4, since it was the last non-zero remainder we encountered. So now we've got that 3x plus 1 is a greatest common divisor. We also have that 2x plus 4 is a greatest common divisor. Now take a notice that 4 times 3x plus 1 is 2x plus 4 in F5 of x. Or 4 times 2x plus 4 is 3x plus 1. 4 is its own inverse in F5 because it's minus 1. And so we've got two different GCDs, but they have the same degree. That shouldn't be surprising. That's part of our definition of greatest common divisor. But they're scalar multiples of each other, or we can get from one to the other by multiplying by an element of the field. Turns out this is not an accident. We say that 3x plus 1 and 2x plus 4 are associates here, and we'll show next week that all GCDs are associates.